Oh, there we go. So video 3 on motion changes, BP3. Hoping this will be, almost guaranteeing this will be the last one. I'm going to make sure it's the last one. So gravity causes things to accelerate at 9.8 meters per second per second. This is from some videos from our gravity lab that things should fall at the same speed because different forces are applied to them. If you took away air resistance. Unfortunately, here on Earth, we have air resistance, so we don't normally get to see that except in vacuum chambers. And air resistance acts in the opposite direction of motion. Friction always acts in the opposite direction of motion. Just mention this one. This one's not as important. Center of gravity not on the test. Vacuum not on the test. So you kind of ignore this slide for the test. Kind of cool to think about, though. Newton's first law of motion. This one is on the test. So according to Newton's first law of motion, unless an unbalanced force acts on an object at rest, the object will remain at rest. And if an object is in motion, it will remain in motion with the same speed and direction. Yada, yada, yada. That's a really long definition. Basically, every object in the universe wants to keep doing what it's doing. So if you have a pen sitting on the ground, not moving, it wants to keep sitting on the ground, not moving. If you have a pen that was shot out of a cannon going 100,000 miles per hour through space, it wants to keep going 100,000 miles an hour through space. Pretty powerful cannon. Whatever. Until something acts on that pen, so until something comes along and pushes it, until something comes along and collides with it, it's going to keep doing what it's doing. If that's not moving, it's going to keep not moving. And if that's moving, it's going to keep moving. That's what Newton's first law says. All objects want to keep doing what they're doing. They're lazy. Sometimes it's referred to as the law of inertia. So that's the tendency for an object to resist changes in motion. Larger objects have more inertia because they just have more mass. Think how easy it is to move a pen versus how easy it is to move a fridge versus how easy it is to move a house versus a mountain. So larger objects just have more resistance normally. Newton's cradle is a pretty typical example of this. I have a real-life version that you're allowed to play with in class. But here you go. The first, if you pick up one side of the ball and let it drop, it wants to stay in motion, but it runs into the other balls, which want to stay still. But because the first object hit them, the other one comes out. So if you go left to right, they just keep transferring that energy. And because there's no air resistance in my little GIF here, it keeps going forever. The one in my classroom, air resistance doesn't keep going forever. Newton's second law of motion. Once again, bunch of words here. Let me summarize this all for you, unless you really want to pause and look at all that down, write all that down. Newton's second law of motion is a formula. Here it is. Force equals mass times acceleration. Apparently it's on the next slide, but this one's still good to write down, so that's why I'm spending a few seconds here. Force is measured in newtons. This is where I said earlier, I think in video 1, what a newton is. It's kilograms times meters per second. Because mass is measured in kilograms and acceleration is measured in meters per second per second. So basically, when you push on something and it actually changes velocity, that's because you applied a force to a mass and it caused an acceleration. There it is. Oh. F equals ma. We used to use these Cheers triangles. They're a different way to look at these equations. I thought I had it here. Nope, I don't have it actually written out. Force equals mass times acceleration. So in my little visual here, small mass, big force, big acceleration. Big mass, same force, small acceleration. There you go. There's your visual. This one's not on the test, but just so you know, like that's how we get our weight. It's actually the gravity acting on our mass. That's the difference between mass and weight. Not testable, but really cool to know. And that's it for our notes. So sorry this one was a little bit longer. There was a lot to get through. We're going to spend a week or two on this instead of 3 or 4 days. So we will get through everything. You will get in-class examples, and you will get practice with all of this. Have a good rest of your day, and I'll see you in class.